Hi class. In today's video we're going to be talking about section 2.4 functions, and I really want to start with this illustration. So imagine you're at an arcade and there's a change machine. Right, you're going to put some number of dollar bills in, and on the other side you're going to get some quarters, right? So this change machine, takes bills and returns quarters, is going to have some input and some output. If you say give it $1, it's going to give you 4 quarters. If you put in a $5 bill, it's going to give you 20 quarters. And if you put in a $10 bill, you're going to get 40 quarters. And I use this example because this illustrates for us the idea of a function. So over here we have our inputs, which we're going to often represent with an x value. And here on the other side we have our outputs, which we're going to often denote f of x. So in this case, our function, which we'll call f, gives us for some input x into our function f, we're going to get an output. And specifically, in this case, we're always going to get 4 times the number of dollar bills we put in, right? So if we put in $1, we get 4. If we put in 5, we get 20, and 10, we get 40. And so a function, we'll call them f, but we can use G, H, I, J, and K, any letter you want, from some set x, and I'm going to put these little bars on my x so that we know that it's a capital X, to another set y, again, put these little lines. So here we have from one set x to another set y is some rule that assigns each element little x in our set x to one and only one element of y. So that means when we put $1 in, we're always going to get 4 quarters. We're not sometimes going to get 3 and sometimes get 5. Or when we put a 5 in, we're always going to get 20. It's not going to give us 4 instead, right? Or 10 is always going to give us 40, not 20, right? So we won't have anything like this, right? We won't have an extra arrow that goes from our 10 down to 20. And so when we talk about these, the set x is called the domain, and the set y is called the range. And I have some more terms to introduce, so let me get another piece of paper. So if f is the name of a function, and x is in the domain of f, remember we use this capital X to denote domain, then the output corresponding to that x is denoted f of x. And so we will say the value of f at x, f at x, f of x. So there will be lots of kind of interchangeable terms. And so if we have a function, you might see it written like this, a function from some set x to another set y, domain, range. These elements look like x, y, z, and they're going to map to f of x, f of y, f of z, something like that. And maybe I don't like this y, I'm going to make it a w, f of w, just because we already used y there. So we can evaluate functions. Right? We often care more about the actual value of the function than our domain itself. And so let's work a little bit with that. So evaluating functions. I'm going to define 3. So we have our function f of x is x squared minus 3x plus 1. Our function g, which is defined as 2 over the square root of x, and our function h, which is defined as the square root of 2 minus x. And my directions say find f of 1, g of 1, h of 1, g of some general a, and g of x squared. So f of 1 says substitute 1 for x. So that means we have 1 squared minus 3 times 1 plus 1. Well, 1 squared is 1. Minus 3 times 1 is minus 3 plus 1. 1 minus 3 is negative 2 plus 1 is negative 1. Negative 1. So we can say f of 1 is negative 1. And if we like our ordered pairs, we would say something like f1, negative 1, where we have x, comma, f of x. G of 1 says substitute 1 for x into this, so we have 2 over the square root of 1. Well, the square root of 1 is just 1, 2 over 1. And we get 2. So we have g of 1 equals 2. H of 1 says take the square root of 2 minus 1. That's the square root of 1, which is just 1. So h of 1 is 1. Now if we want to find g of a, we have 2 over the square root of a. Because all this means is substitute a for x. Or g of x squared, we do 2 over the square root. And now everywhere there's an x, we substitute an x squared. Substitute x squared for x. And so here, we have the square root of x squared. And there's a special property of when we take the square root of a squared. That gives us our absolute value. So for example, suppose now I wanted to find this at 1. We get 2 over the square root of 1 squared, 2 over the square root of 1, 2 over 1, or 2. But if we want to do that at negative 1, we get 2 over negative 1 squared, square root. Negative 1 squared is 1. 2 over 1. So we get the same value. And it always makes it positive. So if we put a negative 2 in, we'll get a 2 out, and so on and so on. So the square root of x squared is the absolute value of x, and g of x squared is equivalent to this form here. Let's look at another example. And I'm going to go back to this previous page just because I have a little bit more room. So let g of x equal 2 times x plus the square root of x squared minus 4. And we're going to find this at g of 0, g of 1, g of 2, g of negative 3, and g of negative x. And so when we find g at 0, we have 2 times 0 plus 0 minus 4 square root. 2 times 0 is 0, plus the square root of negative 4. Well, here we can't take the square root of a negative number. So we can't take square root of negative 4. And so we get that 0 is not in the domain. For a number to be in a function's domain, we must be able to evaluate that function at that point. So what about g of 1? Well, so we get 2 times 1 plus the square root of 1 squared minus 4. We get 2 plus the square root of negative 3. Well, we still can't take the square root. Can't take square root of negative 3. So 1 is not in the domain. So at 2, we get 2 times 2 plus the square root of 2 squared minus 4. Well, 2 times 2 is 4 plus the square root of 2 squared is 4 minus 4 is 0. Well, 0 times 0 is 0, and so we're left with 4. So g of 2 equals 4. And what about negative 3? So we have 2 times negative 3 plus negative 3 squared minus 4. Well, that's negative 6 plus 3 squared is 9 minus 4 is 5. Negative 6 plus the square root of 5. That looks good to me. G of negative 3 plus negative 6 plus the square root of 5. And so if our domain is the set of x values that we can put into our function, the domain, the x values for which the function is defined, the domain of G are all those x such that, you can't see that, is our x such that the absolute value of x has to be bigger than or equal to 2. So here we have all of those x values whose absolute value is bigger than or equal to 2. Because if we put 2 or negative 2 in here, we're good. 3 or negative 3, we're good. But if we put anything like 0 or 1 in, it's not going to work. So it's all of those x such that its absolute value is bigger than or equal to 2. And we'll talk about range in a little bit. But let's go ahead and do the last one. So if we put a negative x in there, what we end up with is 2 times negative x, so negative 2x, plus the square root of negative x squared minus 4. Negative 2x plus the negative x times negative x is going to be positive x squared minus 4 of something like that. Negative 2x plus the square root of x squared minus 4. You're like, okay, so we can have things that look like these equations where we have 2x plus the square root of x squared minus 4. Or we can have x squared minus 3x plus 1. But how else might we be able to define a function? Because when we first started, we had our dollar bills going to quarters. Or we had our, which we then wrote as ordered pairs, right? And so how can we define? Oh, I need another piece of paper. The struggle is real. Give me 1 second. Okay, so we can define a function with ordered pairs. So similar to the one we started with, where we have some a, b, and c in our domain. And then we have some corresponding d, e, and f. As long as each of these goes to exactly 1 on the left, or on the right. I'll put an arrow just to remind us that it goes from x to y. Even if a second element goes to the same right. Or, so we can have 2 elements of x to same element in y, or we can have an element of y with no, so let's call, we can have some element f of x with no arrow into it. But every element of x must go to one and only one element of y. And so we can write these as ordered pairs. So writing these circle diagrams, these set diagrams, are only going to be useful until we have so many. And they get a little cumbersome. So we could say, well, A goes to D. So remember we have x and f of x. We have B goes to D. And C goes to E. But we don't, however, have one element going to a second one. So contrast this with, say, the following ordered pair. 1A, 1B, 2C, and 3D. So what we have here, and we can draw it if we'd like. So we have 1, 2, 3, A, B, C. 1 goes to A, 1 goes to B, 2 goes to C. Oh, and I lost my D. 3 goes to D. This can't happen. This is not a function. It does, however, have a name. This is a relation. So a relation is any rule that maps one set onto another, and that's it. It's a rule that maps them onto it. This is a rule, it maps them on, we have a relation. But a function, remember from our definition at the beginning, it assigns each element of x to one and only one element of y. So because 1 went to both a and b, it's not a function. But even though both a and b went to d up here, it is a function because a only goes to d, b only goes to d, and c only goes to e. So there we have a function. Another reason, so suppose this isn't what I show here, but suppose there's a 4 here and it just doesn't go anywhere. It wouldn't be a function because every element needs to go to an item in the other side. So we can define a function with one of these like set diagrams. We can use our ordered pairs. We can use equations. But we can also use tables and graphs. And suppose we have the following table. We have x and f of x. So suppose -3 goes to -8, -1 goes to 0, 0 goes to 1, 1 goes to 0, 2 goes to -3, and 3 goes to -8. Well, first let's go ahead and plot them, right? Because this essentially gives us a sequence of ordered pairs, -3, -8, -1, 0, 0, 1, and so on. So -3, 1, 2, 3, 3, 4, 5, 6, 7, 8. -1, 0, 0, 1, 1, 0, 2, -3, 3, -8. And I didn't give us a -2 value, but we can connect these. If we can assume that there are points in between. If we can't, so suppose this is literally the entirety of the domain. Is just -3, -1, 0, 1, 2, 3. And our range is literally -8, 0, 1, 0, -3, -8. If this were our domain and range, we couldn't fill this in. And so maybe I shouldn't have. Because we don't know what equation, if any, is underlying this table. Now, I'll give you a secret. It happens to be that there is an equation underlying this, which is why my gut instinct was to draw it. But we'll come back to that in a future video. But most often, sometimes we'll have a table of data. Sometimes we'll have ordered pairs. But generally speaking in this class, we're often going to have an equation, and we're going to want to graph it, and our equation is going to define our function. And so we might have something that looks like this, x equals y minus 1. Well, here we want to know, does every x value go to only one y value? So make a table, x, and actually let's rewrite this. I'm going to rewrite this as y equals x plus 1. And because we want to know if it's a function, we'll use function notation. Does f of x equal x? So does f of x equals x plus 1 define a function? So x and f of x, so let's pick -3, -2, -1, 0, 1, 2, and 3. And it says our function at x is just that x value plus 1. So we have -2, -1, 0, 1, 2, 3, 4. And so let's go ahead and plot those points. So we have 0, 1, 1, 2, 2, 3. And we could also be like, well, we recognize this. This is our linear equation with slope 1. So we can just go up 1, right 1, down 1, left 1, down 1, left 1, down 1, left 1. And even though I only put my points at my integers, we know at -0.5 we're at 0.5, or at 0.5 we're at 1.5. And so we have two questions. Does every x in its domain map to a single y value? Well, what is the domain? Domain. And we talked about domain in a previous section. So domain are those values for which this equation is defined. Well, any number, no matter how big or small, whether it's a whole number or not, I can add 1 to it. So our domain is all real numbers, which looks like from negative infinity to infinity. And our range, if we have a really, really small x, our y is going to be really small. And if we have a really, really big y, our range is going to be, our y value will be high. So we also have all real numbers. So again, we have negative infinity to infinity. So our first question is, does every element of our domain map onto something in the range? And it does. And then, does every element map onto only one element? So, does every x have f of x? And 2, does every x have only one f of x? And in this case, the answer is yes to both. So this does define a function. So let's look at a couple more examples. Suppose we have x, y equals negative 1. And you know I want to rewrite this as y equals negative 1 over x. And here we'll rewrite this in function notation. F of x equals negative 1 over x. So first off, domain. Is there any value that I cannot substitute into this equation? Negative 1 over x. Well, if x equals 0, negative 1 over 0 is undefined. So our domain is from negative infinity all the way up to almost 0, but not including it, together with 0 to infinity. We can write our plus there for emphasis. And we don't know our range, but we can go ahead and plot points. So if x is 1, f of x is negative 1. And so I'm going to, let's pretend that this line, that my axis is on this line here. And I'll use my whiteout to cover up that part that we're not going to count. That's the struggle with trying to write these by hand. There we go. That looks good enough. So at 1, we're at negative 1. At 2, we're at negative a half. At 3, negative a third, negative a fourth, negative a fifth. We're getting closer and closer to 0. But if I'm at a half, I'm all the way down at negative 2. If I'm at a third, I'm at negative 3, negative 4, negative 5, negative 6, negative 7, and so it's getting closer and closer, but we know we can't put a 0 in. And no matter how big we get here, we're going to get closer and closer to that axis, but we're never going to equal 0. And so we can connect it, and it'll look something like that. And then let's look at our left of our 0. So at negative 1, we're at 1. Negative 2, we're at a half. Negative 3, we're at a third. Negative 4, we're at a quarter, a fifth, sixth, seventh, and so on. But at a half, we're at 2. Negative a third, we're at 3, 4, 5, 6, and so on. So it looks something like that. And so here, our range is what y values can occur. Well, here we have all the way from negative infinity, almost up to 0, but not quite. And so we have negative infinity to 0. And then we have to skip over 0 because neither of those will ever hit it. And then here we have 0 to positive infinity. And so that's our domain and range. And then let's look at one more example defined by equation x equals y squared. Well, let's get a y by itself. Y equals plus or minus the square root of x. And if x equals 0, we'll rewrite this f of x plus or minus the square root of x. If x is 0, f of x is 0. If x is 1, we get plus or minus the square root of 1. The square root of 1 is 1. So we get, oh, you can't see that. Plus or minus 1, plus 1, minus 1. If we put in a 4, we get plus or minus 2. 2, 3, 4. Plus or minus 2. 4, 5, 6, 7, 8, 9. We get plus or minus 3. And if we connect those points, we have something that looks like this. And what do you notice? Well, the domain first. We can only take the square root of things as small as 0. So our domain is 0 to positive infinity. And if we go sufficiently far out, our range is going to go between negative infinity and infinity. But if x is 0, right, 0 goes to 0. But if we have 1, it goes to plus 1 and negative 1. And so what do we know is wrong with that? Every x in our domain must go to one and only one element in y. So this is not a function. And if we have a graph, if we would draw any vertical line, so this is the line y equals, nope, x equals 4. 1, 2, 3, 4, x equals 4. It says my f of x is both 4 and f of x is negative 4. Right, that's these 2 points of intersection. This is called the vertical line test. And I want to write your definition for that. If no vertical line intersects the graph at more than one point, then the graph of the relation is a function. So conversely, we say you can draw a vertical line. So yes, you could draw a vertical line at 0, and it'll only hit it once. But it says if no vertical line, so I could draw a vertical line here, I could draw one here, and it'll likewise intersect twice. But if we contrast that up here, no matter where we draw our vertical line, this passes the vertical line test. So this is, in fact, is a function.